So we will look at variance and covariance for two random variables. So you have two random variables x and y, and their joint description is through their joint density function. And from here we can also find out the marginal density functions of x and y. For example, fy would be, you take the joint density function and integrate out x with the proper limits. Similarly, fx will be fxy, and y is integrated out with the proper limits. And if x and y are independent, the joint density function is the product of the marginal density functions. Now, if you recall, so this is the definition for independence. You need to check whether the joint density function is the product of the density functions. And if this relation is true, then x and y are independent random variables. So independence has to do with the density function. But in terms of parameters for a random variable, of course, you have expected value of x, which is the mean of the random variable. Mean is the average value. Similarly, variance is expected value of x minus mu x. So this is the actual occurrence minus its mean. So it's the deviation of the actual occurrence. You square it, and its expected value. So in a sense, this is mean square. If you want to call this as an error, this is a measure of the mean squared error of the observations, error with respect to its average value or the mean. In any case, if you expand this, you get this to be, so you can compute it many ways, or you just do it directly, which is x minus mu x the whole squared fxx dx. So this you can do for x and y. And of course, as we see, if you have a random variable z, which is a scaled version of the random variable, its mean is, you can see, a is a constant, so it's a multiplied by, or its expected value of ax, but a is a constant, so that goes outside. Get a multiplied by expected value of x, which is a mu x. But as far as the variance is concerned, so variance of z is expected value of z minus mu z, the whole squared. But z is ax, so we can write this as ax minus a mu x, the whole squared. So a is a constant. If you pull it outside, it becomes a squared because of the square. And then you have expected value of x minus mu x, the whole squared. But this is the variance of x. So you have a squared sigma x squared. So the interesting thing is variance of ax. If you scale a random variable by a constant, the variance becomes a squared multiplied by the variance of x, not a multiplied by variance, a squared. All right, so this is for one random variable. Now, the question is, so similarly you have sigma y squared. So we have mu x, we have mu y, sigma x squared, sigma y squared, which are all a description of the random variables about x and y separately. Now, to describe them jointly, we could introduce the notion of covariance. So covariance between x and y is defined as expected value of x minus mu x multiplied by y minus mu y. So this, if you expand, there will be 4 terms, and this will turn out to be expected value of xy minus mu x mu y. And so this term is the description about the joint description. So in other words, this term need to be computed using the joint density function. This term minus each of the means x fxx dx minus y fy y dy. So this is the first time we are bringing in some joint description, and why this is called covariance is because if you put y equal to x, this becomes the variance expression. Now using Short's inequality or otherwise, it's easy to show that covariance of x comma y absolute value is less than or equal to sigma x sigma y. So that gives us an idea to define a dimensionless quantity, which is covariance of xy divided by sigma x sigma y. So if you do that, then you can see rho xy is always between -1 and +1. So this is called the correlation coefficient. So conversely, we can also see from there that in addition to this, we have the covariance of x comma y, which you can see we can cross multiply and write this as rho xy multiplied by sigma x sigma y, where rho is the correlation coefficient between. So this is the correlation coefficient. Rho, of course, can be, rho xy can be -1 to +1, including both. So if rho is 0, we call the random variables to be uncorrelated. If rho is 1, then that means x and y are completely synchronous or the coherent. X and y are coherent random variables. So what will be interesting is to take a linear combination ax plus by, find the mean and variance of z. So the mean of z is expected value of, so this is the mean of z. So z is given to be ax plus by. So using linearity, this becomes easy because this is aex plus bey. So this is a mu x plus b mu y. So the variance is a little more work. So variance of z, which is let's say sigma z squared, is variance of z. So that's going to be expected value of z minus mu z, the whole squared, right? But let's substitute for z. Z is given to be ax plus by minus mean, which is already here, a mu x plus b mu y. And I need to square it. And expected value of the square. So I'm going to rewrite it here. So if x and y are so we have sigma z squared. When you expand this, so notice that we can collect the a terms together. So this is the variance of ax plus by is expected value of x minus mu x plus b multiplied by y minus mu y, the whole squared expectation. Because a x minus mu x, b y minus mu y, I just bring it. Now notice that it's like two terms squared. So this, if I expand, this becomes a squared, expected value of x minus mu x, the whole squared, plus 2ab expected value of x minus mu x multiplied by y minus mu y plus b squared expected value of y minus mu y the whole squared. But this term is sigma y squared. This term is sigma x squared. And this is the covariance of x comma y, which as we saw earlier, we can write it as in terms of its correlation coefficient. So here is an interesting, here is the summary of all the results. Okay. So variance of a linear combination is a squared sigma x squared plus 2ab rho xy sigma x sigma y plus b squared sigma y squared. And this is of course going to be positive. So a special case is sum and difference of two random variables. So for example, the variance of sum, so you put a equal to 1, b equal to 1 here. So you get sigma x squared plus 2, a and b are 1, rho xy, sigma x, sigma y, plus sigma y squared. Similarly, the variance of the difference is, the first and the last terms are the same, but b is minus 1, right? So this is 2 minus 2 rho xy, sigma x, sigma y, plus sigma y squared. So if you notice that if you add the variance of this and x plus y and x minus y, the middle term will go away and you'll get 2 times the variance of x squared plus y squared. But here is an interesting observation. Depending on the sign of rho, remember rho could be positive or negative. Suppose rho is positive, then what the last equation says is, if you subtract two random variables, it is possible to reduce the variance of the difference less than the two sums. So because this term is going to be negative if rho is positive, that means the variance of x minus y is going to be less than sigma x squared plus sigma y squared. Now an interesting special case is when x and y are uncorrelated random variables. That means rho is 0, that's what it means. Then you notice that variance of x plus y is sigma x squared plus sigma, because the middle term is 0, but this is also the variance of x minus y. So the result is that when two random variables are uncorrelated, by subtracting the second random variable from the first, you are not reducing the variance. So whether you add or subtract, the variance is still the sum. And as I said, it is possible especially if the rho is not 0, then it is possible to reduce the variance of this by a proper linear combination. So that may take us to a related problem. For example, all right, so for example, or to summarize, if x and y are uncorrelated, then of course the mean is always the mu x plus minus mu y. So if the two random variables have equal mean, you can make the difference have 0 mean. If they have equal variance and if they are uncorrelated, by subtracting you are not going to reduce the variance. In fact, the variance will become double, especially if the random variables are uncorrelated. So for example, variance of 2x plus y, that will be, here a is 2 and b is 1. So that will be from this formula 4 sigma x squared plus 2ab, that will be 4 rho sigma x sigma y plus b squared sigma y squared. So then you can substitute the values. If rho value is given and sigma x, sigma y are given, we can compute the variance of the any linear combination. And an interesting problem in this regard is, suppose you take two random variables, x and y, and construct a new random variable z, such that z is, let's say, ax plus, so z is of the form ax plus y. So the question is, what is the value of a? So find the optimum a that minimizes sigma c squared, the variance of, in other words, variance being a measure of the randomness, we want to select a constant which will minimize the variance. So let's find out its mean. Mean is, of course, a times x plus expected value of y. So this is a mu x plus mu y. And the variance of z is by definition expected value of z minus mu z, the whole squared. But z is given to be ax plus y minus a mu x plus mu y. So we can collect the a terms together as before. So this is a x minus mu x plus y minus mu y, the whole squared. So once again, there are three terms. If you expand this, you get a squared expected value of x minus mu x plus 2a expected value of x minus mu x multiplied by y minus mu y plus expected value of y minus mu y, the whole squared. So this is the variance of y. This is the covariance of x comma y, which is rho sigma x sigma y. And this is variance of, so we get the variance of z to be a squared sigma x squared plus 2a rho xy sigma x sigma y plus sigma y squared. So we want to notice that this is positive quantity and a quadratic. So we are looking for, if you plot this as a function of a, it's a positive quantity. And we are looking for this a. So we can take the derivative of this quantity with respect to z, with respect to a. So that's going to be 2a sigma x squared plus 2 rho xy sigma x sigma y equal to 0. So we can solve for a. A turns out to be minus rho xy sigma x sigma y over sigma x squared. So that's minus rho xy sigma y over sigma x. So that's the optimum value of a. So I'm going to take that optimum value. So that's this a. So I'm going to take that and plug it into this expression. So a squared is going to be rho squared sigma y squared over sigma x squared. This is a squared multiplied by sigma x squared here, plus 2a. A is now rho xy minus rho xy sigma y over sigma x multiplied by sigma x sigma y plus sigma y squared. So sigma x cancels, sigma x squared cancels. Here you have rho squared. Oh, this is all, see, because you have a rho here. So this is also rho squared. So you have 2 rho squared. This is plus, this is minus. So this turns out to be, you have sigma y squared. This is minus rho squared sigma y squared. So this is 1 minus rho xy squared multiplied by sigma y squared. So this is the sigma squared z minimum. So this is this value here. So this is the minimum value of sigma squared minimum. And the optimum A is, so this is the A optimum. Optimum value for A that minimizes the variance for Z. So a related problem is in stock market, like portfolio optimization. So same idea there. Suppose you have 2 stocks and you want to distribute your capital between X and Y. And we want to take advantage of the correlation. So the question is, how do you distribute the money? So you want to put certain percentage. So this, you want to put percentage A here. So A is going to be a number, a fraction between. So whatever is not put here, you put it into Y. So the idea is that if you plot the, so let's say this is sigma x squared with respect to time here. And this is sigma y squared. So both are a lot of variation. The whole idea of designing a portfolio is that the variance of the portfolio, you don't want too much. So this is the variance of the portfolio. You want to minimize the, you don't want to minimize the volatility of what you are holding. This is what you are holding, right? So this is a 2 stock portfolio. So the capital is, this is a fraction here, fraction here. The capital C is 1. So fraction of it is put here. So the question is, what fraction should I put it into stock X? So we can use the same idea here also. Mu Z is A mu X plus 1 minus A mu Y. So the variance of Z is expected value of Z minus mu Z, the whole squared. So if you substitute, this is AX plus 1 minus AY minus A mu X plus 1 minus A mu Y, the whole squared. So once again, if you collect the, so if you expand this, this is going to be expected value of A times X minus mu X plus 1 minus A times Y minus mu Y, the whole squared. So if you expand as before, you can see there are 3 terms. So I'll write down the result here. So this is going to be A squared sigma X squared so sigma Z squared is A squared sigma X squared plus 2A multiplied by 1 minus A rho xy, the covariance, sigma X sigma Y plus 1 minus A the whole squared sigma Y squared. So once again we want, because this is A squared, the variance of X, plus 2A multiplied by 1 minus A, covariance of X comma Y, plus B, 1 minus A squared variance of Y. So if you take the derivative of this with respect to A, you get 2A sigma X squared. This is A minus A squared. Right? So that's going to be plus 2 1 minus 2a rho xy sigma x sigma y plus 2 multiplied by 1 minus a and with a negative sign, minus a. So that's minus sigma y squared. This should be equal to 0. So notice that one set of 2 goes away. So you have, if you collect all the a terms, you have, or you can solve for a. All right, so the constant terms that goes to the other side are here minus, so sigma y squared minus rho xy sigma x sigma y over sigma x squared minus 2 rho xy sigma x sigma y and sigma y squared from here. So you can see this is clearly less than 1 because the denominator terms are, you have sigma y squared minus rho x sigma x sigma y here plus sigma x squared minus rho xy sigma x sigma y. Anyway, here is the value of a. Now, this a, there could be cases where this a could go negative, in which case, in terms of investing money, it doesn't make sense. So those are not the right stocks, or you have to do some other additional optimization. But this, if this a turns out to be positive, then this will be a fraction. And if a is a fraction, 1 minus a is a fraction. So that means if this turns out to be 0.3, this will be, you put 30% of the money into the X stock. And so right, this calculation is right? Because see the other side you have minus sigma y squared, right? And another term here is see plus rho xy, which it goes to the other side, you have minus, right? And the denominator you have a terms are sigma x squared minus 2 rho sigma x sigma y and minus minus plus sigma y squared. So that's, so a is this. So this need to be checked. And then you can substitute that value for a into this and also find out what is the minimum, minimum value of the variance. So the idea is by putting this, you reduce the volatility of what you are holding. Remember, you are not interested in the whole market. You are only interested in what you are holding, which is the portfolio. You want its variance to be, its fluctuation to be as minimum as possible. So again, you can see the A is, the correlation is used to take advantage of the flexibility. So a special case, suppose they are equal variance, then all the, so if, for example, if sigma x squared equal to sigma y squared, then A will turn out to be, remember, this is equal to sigma squared, then sigma squared goes away, you have 1 minus rho xy over 2 multiplied by 1 minus rho xy, and this means half, right? This is 1, this is 1. These things are all sigma squared. So 2 minus 2 rho xy. So which means that if they are equal variance, and another interesting thing is, it doesn't matter what the correlation is, put 50% of the money into each one. So if you want to exploit, if you want to diversify, you want to put your money unequally, then you need to look for two stocks or entities which has got unequal variance also. Right? And Another thing you can see for surely is, suppose rho is negative. Remember, if rho is positive, as I said, it's conceivable that this quantity could go negative and it doesn't make sense. But on the other hand, if rho is negative, which means x and y are, when x goes up, y has tendency to go the other way, then minus rho will be positive. Then the numerator will be positive, denominator will be positive. Numerator is less than denominator, so a is guaranteed to be between 0 and 1. So you can see if rho xy is less than 0, that means x and y are negatively correlated. When one goes up, the other one goes down. Then you can see a is guaranteed to be a fraction, and a is between 1, because this minus rho will be positive, this is positive, all these are positive. Positive over a larger positive, because the denominator is not only this, you are adding more positive terms. So this is a fraction, less than 1, right? You see that, right? So then a is between 0 and 1. So this technique will lead to the right solution. Since you are free to invest anywhere you like, so if you can figure out two quantities which are going in the opposite direction, then the optimum solution, then there is no other headache. A will turn out to be a positive fraction, and the actual value of a will depend on not only the correlation but also the variances. As I said, if they have equal variance, then this strategy is useless, because it's not exploiting, it is unable to exploit anything, because it says invest the money equally, irrespective of the correlation. So that's not that intuitive in the sense of, so you may say, why are we not able to exploit the correlation? So the moral of the story is, with the two, if you're only dealing with the two stocks, even though they are negatively correlated, you do want the variances to be unequal. And as I said, now you can you take this value and plug it in here, you can find the minimum value of variance.